Okay, let's get started. So we'll begin the lecture going through the quiz solutions. Okay, they have been posted on Learn, so you can read through them there. But if you have any questions as I'm going through it, please just let me know. Okay, so the first part on the odd and even functions, we were given that f was an odd function and g was an even function. Then we were given a new function h, and we wanted to know, is it odd or even? Okay, so in the first case, h of x was given by f of g of x plus f of x. Okay, now we should know what composition means. So f of g, you put g inside f. Okay, that's the definition that we went through. So h of x, that's going to be f of g of x plus f of x. Okay, so writing it like this makes it a bit easier to work out if it's even or odd. Okay, there is only one way to test if it's even or odd. If you have f of minus x being equal to f of x, it's even. If you have f of minus x equaling minus f of x, it's odd. That's it. That's all you need to check for. So here we're testing if this is odd or even, so h of minus x, that's f of g of minus x, not f times g. Too many students are writing f times g. It is composition, not multiplication, plus f of minus x. Now we simplify. So g is even, so g of minus x is g of x. So this is f of g of x. F is odd, so f of minus x is minus f of x. This is not h of x, so it's not even. Simple as that. Okay, in the second case, we had h of x. Sorry, do you have a question? Okay, h of x, this was g of f of x minus g of x. Okay, we want to test, is this even or odd? There's only one way to do that. You have h of minus x and you see what you get. So h of minus x, what do we have? Okay, so this g of f of x, that's going to be g of f of minus x minus g of minus x. Okay, f is odd. F of minus x is minus f of x. G is even. G of minus x is g of x. Okay, again, g is even. G of minus f of x is g of f of x. We get back h, so it's even. Okay, so not even and even. That's it. So if you want to do it like this, that's fine. If you wanted to explain it, that's fine as well. So for the first part, you could have said f of g of minus x, f of g of x, that's even. F is odd. Even plus odd can never be even, so it can't be even. In the second case, g of f of x, that's even. G is even. Even plus even is even. We covered that in class. So you could have said that as well. So you either do all the working to test if it's even or odd, like this, or you just say odd plus even, not even. Even minus even is even. That's all you needed to do. Okay, for the decomposition, all you needed to know was the formula. So for the, yes? Okay, so we have g of f of minus x. F is odd, so the minus comes out. G is even, so it becomes g of x. So we have this and we have this. G is even, so g of minus f of x is g of f of x. That stays the same. This is exactly what we started with, so it's even. Okay, so if we want f even, okay, that's 1/2 f of x plus f of minus x. Okay, we derived this and proved this in class. You don't need to redo all of that. You can just start with the formula. We're given f of x. All we needed to do was substitute. So this is going to be 1/2. F of x is just what's given. You don't have to do anything else. You just write exactly what it says. Okay, f of minus x. Wherever you see an x, you put a minus x. So that's minus 2x minus 1 over x plus 3 to the minus x. 2x minus 2x cancels, 1 over x minus 1 over x cancels. So we have 1/2, 3 to the x plus 3 to the minus x. Okay, that's it for the even part. For the odd part, very similar. You just need to use the formula again. So that's f of x minus now, because it's odd, f of minus x. And again, you just substitute exactly what's given. So f of x, straight from the question, you just rewrite it. That's 2x plus 1 over x plus 3 to the x. Minus f of minus x, you put in f of x, but wherever you see an x, you put a minus x. So that's minus 2x minus 1 over x plus 3 to the minus x. Okay, exactly like we did on the previous Thursday. Okay, so that's 1/2. 2x plus 2x, that's 4x. 1 over x plus 1 over x, that's 2 over x. And then we have 3 to the x minus 3 to the minus x. Okay, the half cancels a few things, so we're left with 2x plus 1 over x plus 1/2, 3 to the x minus 3 to the minus x. Okay, and that's it for the odd parts. Okay, exactly the same as we did on the Thursday. Okay, so that was the first part. For the second part was on the domain. Okay, some people were finding the domain and the range. The question just said find the domain. Don't do extra work if it's not needed. Okay, so for the first one, we have f of x is equal to 1 over absolute value x, and g of x, that was sine x. Okay, and we wanted the domain for f of g of x. So f of g of x, that's going to be f, and inside f we put g. F of g, so inside f we put g. Okay, so this is going to be 1 over absolute value sine x. Why? Because we take g, we put it inside f. There's no other way of doing that. Okay, the domain, we look at this and see where does this go wrong. We have 1 over something. It goes wrong when that something is 0. So we look for where that something is 0. Okay, where it's 0, that's the problem points, we throw them out. Where is this 0? It's at 0, 180, 360, ... So you can put it in degrees, that's fine. For the test, remember we're working in radians. In radians, that's 0, pi, 2 pi, ... Okay, so those are all the positive ones. We include all the negative ones. So in the end, the domain we can write as everything but not those. So x is not a multiple of pi. Okay, or 180, but we're trying to move into the radians part. Okay, so that's the domain. Everything except where there are problems. There's problems where sine is 0. When is sine 0? Look at the graph. 0, 180, 360, and then you can add any multiple of that. Okay, so that's for the first one. For the second one, we have f of x is 1 over root x. Here you've got 2 alarm bells going off. Number 1, there's a root. You can't take the root of a negative. Number 2, we're dividing by something. You can't divide by 0. You should be thinking of that immediately. Okay, and then g of x, that is 2x squared minus 3x plus 1. Okay, just a normal parabola. Nothing wrong with just a parabola. Okay, f of g of x. We take g, we put it inside f. So we take g, we put it inside f. So we get 1 over the root 2x squared minus 3x plus 1. Okay, a lot of you were swapping that around. If it's f of g, g eats up the x first and then goes into f. If it's g of f, f eats up the x first and then g. Okay, please do not swap those around. F of g, g comes first, so that's the inside part, f is the outside part. Okay, again, we ask ourselves, where does this go wrong? In other words, where is it undefined? And then that is not part of the domain. So we've got a root. First of all, the inside part cannot be negative. Okay, so we'll check for that. We're also dividing by it, so it can't be 0, right? Because you can't have 1 over 0. So let's see where it's 0, and then we'll see where it's negative. So 2x squared minus 3x plus 1 equals 0. Okay, you find where it's 0, those are the problem points. You end up with 1/2 and 1. Okay, so we can just draw a picture of this. It's a happy face, smiley face, parabola, so it looks something like that. Here's a half and here's 1. Okay, at those two intercepts, it's 0. So we need to throw those out. So x equals a half, throw out, x equals 1, we have to throw out. Between those 2 points, the function is negative. It's below the x-axis, so it's negative. We need to throw that out. Why? Because number 1, we're dividing by something, it can't be 0. Number 2, we're taking the root of something, it can't be negative. So we throw out the points where it's negative, we throw out the points where it's positive, where it's 0. Okay, so what do we throw out? A half and everything up to 1. That's where it's negative, we throw it out. So we can look at everything, but not that. So x is not an element of 1/2 to 1. You can write it like that if you want, or you can write it as just the union of the rest of it. If we throw out the middle, we're left with either end. So minus infinity to a half, and then from 1 to infinity. There's a number of ways of writing it. As long as you have something like that, it's fine. Okay. And then the last one, we have f of x is equal to 1 minus x, where x is less than or equal to 0, and 1 over x when x is greater than 0. Okay, top part, 1 minus x, that's a straight line. No problem with the domain, it can be anything, we can ignore it. 1 over x, there's a problem at 0. Well, let's look at the domain for that part. X greater than 0, okay, there's no problem. Why? Because that second part, that subdomain, doesn't have 0. So there's no problem there. Make sense? Okay. So always have a look at what you're working with before answering. G, that is x squared plus 1. Okay, just a parabola, no problem with the domain. There's no asymptotes or anything like that. Okay, f of g. You take g, you put it inside f. Okay, like you did with those tutorial problems. So f of g, we take g, we put it inside f. Like literally, it goes into f like that. Okay, so this is going to be a piecewise function. Why? Well, f was a piecewise function. If you substitute something, it's still piecewise, that doesn't change. Okay, 1 minus x, that's going to be minus x squared. Okay, the domain doesn't change, it's still f, we're just putting something inside there. So that's x less than or equal to 0, and then 1 over that. Okay, make sense? Okay, are there any problem points? The top, minus x squared, that's a parabola. No asymptotes, no problem. Okay, 1 over x squared plus 1. We have an issue if that bottom is 0. X squared is always positive, and now I'm adding 1. If I have something that's always positive and I'm adding 1, it's even more positive than what we started with. So that bottom part can never be 0. Even if it could be, x is greater than 0, so we know it's positive. That's part of the domain written there, x greater than 0. Something positive plus 1 is even more positive. No issue with the domain. Okay, so how do you find the domain of a piecewise function? Domain for the first bit, union domain for the second bit. right? We did that on Wednesday. Okay, the first one is everything smaller than 0 and 0. The second bit is everything bigger than 0. So altogether, everything smaller than 0, 0, everything bigger than 0. Well, that's everything. Okay. You didn't even need to write f of g. The domain's given in f. There's f there. X being less than or equal to 0, that's the subdomain. X greater than 0, that's the other subdomain. It includes everything, so the domain is everything. Okay, if we substituted something funny like 1 over x minus 1 or something, then there's problems. We're substituting something where there's no problems. It's just a parabola. So we're not adding any issues to it. So the domain stays the same. Okay, any questions on that? Okay, please go through this. Please go through the memo. Rewrite the quiz if you need to. But whatever mistakes you made for the quiz, please do not repeat them. Okay, learn from your mistakes. Okay, even if you got a terrible mark, that's fine. There's still more to come. But if you don't learn from your mistakes, then that's a problem. Okay, remember we're taking the top 10 quizzes. So, we can ignore this one if it's bad, that's fine. But if you ignore it and you don't learn from it, everything else is going to be bad. So rather stop with the bad stuff now and work on the next bit. Okay. So everyone agree with me? You're going to work on it for the next time? Okay. Yeah.
No practice something or like anything that we can do just to practice.
So the homework stuff, that's good practice, and the tutorials. That's all you really need. If you need anything else, you've got the textbook. There's plenty questions there. But like at a minimum, if you can do the homework and the tutorials, you can write the quiz. If you want to be a top student, you go to the textbook and you do more. James Stewart Calculus. Yeah, the PDF is available, so you can work with that. If you don't like that for any reason, you can come to my office. I have the actual book. You can spend an hour taking photos of the exercises if you want. That's fine. But there is the PDF there. Okay. Anything else? Yeah. Quizzes. We'll see how many we can do. So at minimum 10, if we do more than 10, I'll take top 10. So if we do 12, we can forget about the worst 2. Okay. So, yeah, it's not all bad. We do have more coming. But please learn from your mistakes. Don't just throw this one away because you did badly. Learn from it so that you can do well in the next one. Okay. Also remember the class test is coming up. 11th of March, I think it was. 12th March, yep. Okay, yeah, you know the date now, so no one can say you don't know. Okay, 12th March. Okay, I'll get to the scope now. So we're going to go up to limits. That's the next thing for next week. It's only going to be up to what we cover this week. Okay, so this beginning bit on inverse functions, that's the endpoint for the scope. Okay, limits, which we're doing later on, that will be in the following test. Okay. Everyone all right with that? Okay, so let's start on the new stuff. This will be the last bit for the class test. Okay, so what we do next week, that won't be in the class test, that will be in the following class test. But remember, for the June test, June exam, that is on everything, from the beginning right to the end for the semester. Okay. Okay, so inverse functions. Okay, so there are 3 properties of a function that we need to go through. Number 1, injectivity. Number 2, surjectivity. Number 3, bijectivity. Okay, so they have awful names, but we're just going to go through it like we did with functions. We're going to start with the picture of what a function is, I'm going to show you how this property relates to the picture, and then we'll move on to the more advanced way of writing it. Okay, so the first thing, injectivity. Okay, so this is just a property that a function can have. So if you give me a function, I can say, yes, it's injective, or no, it's not injective. Just a property, like, is it a parabola or is it not a parabola? Something like that. Okay, so the easiest way to explain this is to go back to those pictures of sets that we had before. So let's say we have a set X, and we have a set Y. Okay, right back at the beginning, this is how we introduced functions. This can have x1, x2, x3. Okay, y, we can have y1, y2, y3, y4. Something like that. Okay, and a function is a mapping from x to y, so we can draw the arrows. Okay, so this was just something easy. So x1 goes to y1, x2 also goes to y1, no problem with that, and x3 goes to y3. So we know the domain, we know the range, we know the target. Okay, so everyone should be comfortable with that. Okay, so what does it mean for a function to be injective? Okay, so we'll start with the definition, and then I'll show you how it relates to this picture. So we say that a function is injective if we have f of a being equal to f of b, so two elements being the same in the target. F of a is equal to f of b. You can think of it like y1 being equal to y2. Okay, two elements in the target, they're the same. If this means that a equals b, so those are your x values, then we say that it's injective. Okay. So in this case, here we have x1 going to y1. We also have x2 also going to y1. This is an example of a function that is not injective. Why? Because look at the definition. If f of a is equal to f of b, then the a and b must be the same. Here, just in terms of the picture, we have y1, but x1 goes there, right? And x2 goes there, but those are different. This says that they should have been the same. Okay, so if you have some elements in the target, two elements in the domain mapping to it, it is not injective. Okay, so if you have a picture like this, this is how you can tell if it's injective or not. If you've got 2 to 1, like that, okay, you might have heard that before. Okay, two elements going to one element like this, it is not injective. If it's one element going to one element, then it is injective. And that's another name for injectivity. You might see it as 1 to 1. Okay. So this example over here, this is not injective because it's many to 1. In this case, it's 2 to 1. So here, x3 goes to y3, that's fine, but that doesn't prove anything. The fact that we have x1 and x2 going to the same element, okay, not injective. Okay, so a couple examples on this. So firstly, an example, and then a non-example. Okay, so a straight line. Okay, this, whatever straight line, doesn't matter. This is an example of an injective function. One x value goes to one y value. So it's injective. Okay, and then a non-example, just to help that, a parabola. If we draw a horizontal line here, these 2 points here, they're different points. They share the same y value, but I chose them differently. Okay, so they share the same y value and they have 2 different x values. So here, this x1 gets mapped to y, just by looking at that. And this x2 gets mapped to the same y value, right? Because it's on the same horizontal line. So the same y value is reached by two different x values, right? They're different. One's on the one side, one's on the other side. They're different. So this is not injective. Why? Two x values gave us the same y value. So it's many to one, so certainly not 1 to 1, so not injective. So a straight line, injective. This parabola, not injective. Okay, so this is looking at it in terms of the graph. So we've got two ways of looking at this so far. Number one, elements mapping to elements. So you can have two elements mapping to one element, not injective. You can look at it in terms of the graph. One x value goes to one y value in a straight line, but with the parabola, two x values go to one y value. Okay, so it's not injective. Okay, and then the third way, if you don't want to sketch it or anything like that, you can do it algebraically. So let's say we have a function f of x equals 3x plus 1. Okay, we know it's a straight line, it should be injective. Let's show it's injective. How do we do that? Well, we go to the definition. If f of a is equal to f of b, then a must be equal to b. That's what we want to show. If that is true, then it's injective. If it's not true, then it's not injective. So let's see. We start off with f of a being equal to f of b. Some amount of working later, we should get a equals b. So let's see that. Okay, on the one side, f of a, wherever we see an x, we put an a. So it will be 3a plus 1. On the other side, we have 3b plus 1. Okay, good. This doesn't prove it yet. We still want to show a equals b. We have a 1 on both sides. We can get rid of that. Right, it's an equation. Whatever you do to the one side, you do to the other side. Standard stuff. So 3a equals 3b. Okay, good. Now both sides have a 3. We can get rid of that. Okay, divide both sides by 3, or times by a third, however you want to think about it. A equals b. And we're done. So we started with f of a equals f of b, something, 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 a equals b. Okay, the middle part doesn't matter so much. As long as we started with f of a equals f of b, we showed that a equals b, so it's injective. Okay, so from here to here, we know that it is injective. Okay, let's look at another example, or should I say non-example. Let's say f of x is equal to 3x squared. Okay, now we already know parabolas aren't injective, but let's see what goes wrong with this idea of f of a equals f of b. Okay, so f of a equals f of b. Okay, we substitute, so we get 3a squared equals 3b squared. Okay, that's fine. We can divide both sides by 3. Okay, now at this point it's very easy to make a mistake. If we take the root on both sides, you might say that a equals b. But if you take the root on both sides, you're throwing away two solutions there. Okay, you can't just take the root like that. Let's do it a bit more carefully. Please do not take roots on both sides. It will cause problems. Do it this way instead. Okay, so what we do is we take everything over to one side. Okay, no roots needed, no problems there. Now we have a difference of squares. We can factor it. So we get a plus b, a minus b. Right, your dots from high school. Okay, still no roots. I've done no roots here. I've just factored. We've got a product of two things being 0. So either the first thing is 0 or the second thing is 0. Right? Okay. If the first thing is 0, a equals minus b. If the second thing is 0, a equals b. So a equals b, we would have gotten that from doing the whole root, but we're missing out on this a equals minus b. The fact that a equals minus b is a solution means it's not injective. Why? Well, because a equals minus b, not a equals b. We wanted a equals b. So this bit here, this is the extra solution that we got from that picture. So here, if we see this picture here, okay, we've got the solution on the one side, okay, that's fine. There's also a solution on the other side. If you just take the root, you're throwing it away. Okay, so here we get both. Okay, so it's not injective. Okay, any questions so far? Okay, homework problem. Okay, find k, such that f of x equals x cubed plus kx plus 1 is injective. Okay, there might be one value of k, there might be a few values of k, but that's our function. We want it to be injective, so what does that k have to be? Okay, something you can do as well with this, you can plot this on Desmos with the k being a variable, and then you can change it. So plot it with k being allowed to change it and see what the function looks like. If you ever get to a point where it looks like this, right, that horizontal line cuts through 2 points, if it ever looks like that, it's not injective. Okay. If you have a horizontal line and it only cuts at 1 point, then it is injective. So you can plot it for different values of k, and then you'll see at some points it's injective, other points it's not injective. Where is it injective? Okay, so find those k values. Okay, is everyone comfortable with this idea of injectivity or one-to-one? Okay, so you've got a function, one input goes to one output. If that's the case, it's injective. Okay, so the name might be a bit scary, but just think one-to-one. Okay, next, surjective. Okay, again, scary sounding name, but this is very, very simple. Okay, it's the easiest one out of the three. Okay, so like we did for injectivity, we start off with a picture of the sets, and then we'll go through the definition and why that works. Okay, so we've got a set x, we've got a set y. So we have x1, x2, x3, y1, y2, y3, y4. Okay, why not? Okay, so those are our two sets. Now we need a function between the sets. In this picture form, the function is just arrows from the domain to the target. Remember, we have to use everything in the domain, and it needs to map to something in the target. The stuff that it does map to, that forms the range. The stuff that it doesn't map to, well, that doesn't matter. Okay, so let's say x1 goes to y1, x2 goes to y3, x3 goes to y4. Okay, that's my function. I've got my domain, I've got my target, I've got my range. Perfectly valid function. In fact, it's an injective function. Why? It's one-to-one. Okay. Now, the idea of surjectivity is that for every element in the target, there is something in the domain that gets mapped to it. Okay, so I'll repeat that. For every element in the target, there is something, one thing, maybe more things, something in the domain that allows you to map to it. Okay, something, right? It can be one thing, can be more than one thing, doesn't matter. Okay, so let's go through this picture here and see, does this satisfy the property? So for every element in the target, well, let's just go through the list. It's a finite list. Okay, y1. Is there something in the domain that allows me to map to y1? Is there? Yes. x1. Doesn't matter what it is, but there is something. It exists. It's over there. Okay. y2. No. y3. y4. Is this surjective? Who says no? Who says yes? Who's not going to do well on the next quiz? Okay. This is not surjective. Why? Because it's all the elements in the target that we're looking at. We need to look at all of them. y1 works. y3 works. y4 works. y2 doesn't work. Immediately, not surjective. You just need one thing to go wrong and it doesn't work. Because it's for all the elements in the target. If one of them doesn't work, well, it doesn't work for all of them then. So it doesn't work at all. Okay, so this is not surjective because y2 has no partner in x that allows me to get there. Okay, so first one, not surjective. Let's look at another one. We've got x, we've got y, same sort of thing, x1, x2, x3, y1, y2, y3, y4. That goes to there, that goes to there, this goes to there, let's put an x4, that goes to there. Okay, so we've got something like that. Let's put an x5. Okay, that goes to there. Okay, a bit more complicated, but that's fine. We can just follow the arrows. Okay, x1 goes to y1, x4 goes to y2, x3 goes to y3, x2 goes to y4, x5, I think I missed out, goes to y4. Okay, so we got all the arrows. We can read that. Okay, remember the definition. For all elements in the target, there is something, maybe one thing, maybe two things, doesn't matter, in the domain, such that we can map to there. Okay, y1. Is there something in x that maps to y1? Yes. y2. y3. y4. In fact, y4, there are two things. Doesn't matter. We only need one. At least one. If there's two, that's fine. There must be one. So is this surjective? Is it injective? No. Why? Many to one. Good. So this is an example of a function that is surjective but not injective. Okay, so you can have one or the other. You can have both or neither. Okay, so this is surjective. Okay, so now I'm going to write it algebraically and then we can work out is it surjective or not. Okay, so by algebraically I mean the old way we write it, name of the function, domain, range, target, and the rule. Okay, so f goes from R to R, x goes to 3x plus 1. Something simple. Okay, we've got the domain, we've got the target. What's the range going to be? Real numbers, yeah. Okay. Now notice that the range is all of the real numbers, and the target is all of the real numbers. Okay, so the range is equal to the target in this case. Okay, so let's look at the range. For every, let's look at the target. For every element in the target, is there something in the domain that gets mapped to it? Yes. Why? Well, because the target is equal to the range. The range is everything that we map to. If everything that we map to is equal to the target, well then we've mapped to everything. And if we've mapped to everything, everything in the target must have come from something. Does that make sense? Okay. No, doesn't make sense. Okay, here. So we've got y, 1, 2, 3, 4. Did we leave anything out? No, we didn't leave anything out. So if we go through all of those things, they must have come from somewhere, right? And if they came from somewhere, it's surjective. If we left something out, if there was a y5 here, y5 is in the target, but not the range. So it's not surjective. But we didn't leave anything out. So it is surjective. Okay. So you can think of surjectivity as look at the range inside the target and see, did we leave anything out? If something is left out, it means there's something that we don't map to, right? Well, then it can't be surjective if we don't map to it, right? We need to map to everything in the target. Okay, so in this case, this is surjective, right? Because the target, the R over there, is equal to the range. The range is everything. Okay, so let's look at something like this. Yeah, something like that. We've got the domain, we've got the target. We don't have the range. You're going to find that. What is the range of this function? Yeah. Okay, what's the range? Positive, yeah. It will be from 0 to infinity. Just look at the picture. It goes from 0 to infinity. So that's the range. We can write that as f of r. Okay, that's the range. The target is all of r. Okay, so now all we're looking for is one element that's left out. If we find just one that's left out, it's not surjective. Remember again the definition. For all elements in the target, if there's one left out, it is not surjective. It has to work for every single one. Okay, there's the target. I can just find one that it doesn't work for, not surjective. So I'm going to pick one. You tell me, does it work or not? Okay, if I choose the number 4, is there something in the domain that gets mapped to 4? What is it? 2. Or? Yeah, you only need 1. That's fine. 1. 1, also minus 1. Doesn't matter. Okay, negative 2. No, nothing. Nothing gets mapped to negative 2. Nothing gets mapped to negative 2. Right? Negative 2 was in the target, but nothing got mapped to it. Or if nothing mapped to it, it's not surjective. Okay, not surjective. Make sense? Yes? No? Okay, mixed signals going on here. Hands up if you don't understand. You let me go through the whole example and then you tell me you don't. Okay, where did I lose you? Okay. Okay, this first R, what do we call that? Okay. What do we call this? Okay, as a set, this function whole set. This is the domain. This is the target. What's the range? The range and the target are different, right? We covered this before. The target is given, I give you the target over there. What's the range? 0 to infinity, that's the range. If I look at the range and I compare it to the target, is there stuff in the target but not in the range? Minus 2. There's minus 2 here. Real numbers, all the real numbers. Is minus 2 here? Yes. Is minus 2 in the range? No. It's not surjective then. We have found something in the target that's not in the range. So it's not surjective. Does that make sense? Okay. All you need to do is find one point where it doesn't work. One point that's in the target, but not the range. Then it's not surjective. Yes? The target is what I give you. It's part of the function. I could give you a different target. This is just from the example. Remember what we had at the beginning when I talked about functions. A function has a domain, a target, and a rule. Those three things I give you, right? I give you the domain, I give you the target, I give you the rule. The range is something else that you can find. Sometimes the range matches the target, sometimes it doesn't. If the range matches the target, if those are the same, then it's surjective. If the range does not match the target, then it's not surjective. Does that make sense? Okay, let's have a look at another example. Okay, so we have F. Okay, this is all the information I give you. There's the domain, there's the target, there's the rule. That's all you need to work with. Okay, now we want to know, is this surjective or not? What do? We go through everything in the target and see, is there something in the domain that gets mapped to it? In the previous case, we found minus 2 does not have a partner x value, so it's not surjective. Let's go through everything in the target and see, can we find something in the domain that gets mapped to it? Okay, well, let's just go through everything. 0. Is there a partner x that gets mapped to 0? Yes, what is it? 0, fine. Okay, let's pick 1. 1 is in the target. Is there something in the domain that gets mapped to it? Yeah. What about 2? 3? Anything there? Is there anything left out? Is it surjective? Okay. Now, can I pick minus 1 from the target? No, it's not there. There's the target. So we don't have that problem. In the previous case, I could have picked minus 1 because that was in the target. I said the target was real numbers. Here, I don't have the problem. Right? Okay, so in this case, it is surjective. Okay, making more sense now? Okay, so a very quick way of taking a function and making it surjective is to replace the target with the range. Remember, the target is what you choose. I chose that. Okay, doesn't have to be that, I picked it. Okay, if I give you a function and I say, make it surjective, you don't need to change anything else. The target, you redefine the target to be the range. Then the target equals the range. Nothing's left out, it must be surjective. Okay, so easy way to make a function surjective. Okay, so let's say we have f going from x to y with some rule. X going to f of x, whatever that might be. Okay, now how do we check if it's surjective? We need to go through everything in y and check, is there an x that gets mapped to that? Okay, so it's quite a mission. Now I can just redefine it, that's fine. So I give you, or you give me, a new function. Let's call it f, the little hat. But now the target, I define that to be the range. That's fine, it's a new function, that's what I call it. Now it is immediately surjective. Why? Because I have to go through everything in the target and check, is there something that gets mapped to it? But now the target is the range. And by definition, the range is everything that has something mapping to it, right? If we have a y value that doesn't get mapped to, well, it's not part of the range, so it doesn't matter. Okay, but here, everything works out nicely. This is automatically surjective. So if the range is equal to the target, we've left out nothing, so it is surjective. Okay, one more example. Okay, let's have f going from r to 0, 1. X gets mapped to root x. Okay. Firstly, what's wrong with this? There's something very, very, very wrong with this. Okay. Anyone would like to answer? Sorry? No, it's not the range. The range is fine. The target's fine. Something with the domain. Yes? Yeah. Yeah, real numbers include negative. The negative values are in the domain. I can't put that into root x. That doesn't work. Okay. So that doesn't work. Okay, so what I can do, just a little bit of notation. I can call it r plus. Now we only include the positive. Sometimes you'll see this with the little star. Okay, sometimes with the plus. Okay, so it's fixed now. Okay, so now I'm only including positives, which is good because I'm taking the root. Okay, now we can ask ourselves. Firstly, let's ask if it's injective. Is this injective? Think about what it means to be injective. Okay, is this injective? Yes. Okay, you can do a little sketch. Draw a horizontal line. If it cuts at one point, it's injective. This does. Okay, is it surjective? I heard some no's. Let's go through the set. Okay, what does it mean to be surjective? For every element in the target, there is something in the domain that gets mapped to it. Okay, so let's see. In the domain. Okay, so this goes to the next issue. We fixed the domain, now we're going to fix the target. Okay, we want this to be surjective, that's the goal. Okay, if I pick 0, is that fine? Okay, if I pick a half, who said no? Someone said no. If I pick half, does that get mapped across? Yes. Okay. What about 1? 1 works. Yeah, that's fine. What happens when I pick 2? Okay, I'll pick 2 from there. That's part of the domain. That's fine. I pick 2. That goes to root 2. Where is that? Is that in the target there? No. So what do I need to do? I picked that as my target, but we've come across a problem now. So what can I do to fix the target so that it now becomes surjective? Okay, because we've already picked the domain. Okay, we can leave like that. Okay, but that target there, what do we do? Okay. Okay, think about it. What does it mean to be surjective? Everything in the target has something in the domain that maps to it. Okay, we use everything in the domain, so we can pick 2. 2 goes to root 2, but it's not in the target there. So what's the problem with the target? Okay, I picked it, but there's a problem, right? We want to fix this. What's the problem? Anyone? Okay, please go back to your notes before when I spoke about domain and target and range if you're not following. Okay, I picked x equals 2. That gets mapped to root 2. Is that in the interval? No. So what's the problem with the target? It's too small. The target doesn't cover everything. So what can I do to change the target so that it now becomes surjective? Change 1 to infinity. Good. Okay, so here I can have f. Okay, r plus, that will be 0 to infinity, 0 to infinity. X goes to root x. Okay, I've just rewritten the r plus there. Okay, any more problems with this? No, everything's fine. Okay, so do you understand where things can go wrong and why we choose certain things? Okay, please make sure you understand domain, target, and range. This is not just like high school where you had a function going from all real numbers to all real numbers. We need to be very careful about the domain, the target, and the range. Like here, it looks fine. It looks fine there, but there's a problem. You can't just look at that and say, okay, it looks fine. Right, look at it very carefully. What goes wrong with the domain? What goes wrong with the target? You need to be very careful with that. Okay, but this is fine. Okay, is this injective? Yeah, and now it's surjective as well, so that's good. Okay, any questions on this? Okay, please, does everyone understand why that target was wrong? Okay, don't sit here not understanding it and then you come to me next week. Okay, that's too late. Does everyone understand why we had to change that? Okay. Okay, so that's surjectivity done. The last thing is bijectivity. Okay, so this is very easy. If a function is injective and surjective, we call it bijective. Okay, so bijective equals injective and surjective. Okay, both need to be true, then we call it bijective. Okay, so same as before, we're going to start off with the set picture with the arrows to understand it, and then we'll go on to the algebra part. Okay, we've got a set x, we've got a set y. Okay, we're going to have 3 elements here, x1, x2, x3, y1, y2, y3. Okay, we're going to build up this function such that it is injective and surjective. And we'll see something very special happens in that case. Okay, so firstly, it's a function, so everything in the domain needs to be used. So x1, x2, x3, we have to use all of those. That's a given. Now, we want it to be surjective. Everything in the target must be used. So y1, y2, y3, that must also be used for it to be surjective. Nothing left out. If we had a y4 and we left it out, it's not surjective because we left it out from the mapping. Okay, so that handles the surjective part. Everything in y we're going to use. Next, for injective, it must be 1 to 1. So I'm going to pick an x value, and I'm going to pick one and only one y value for it to map to. So x1, let's put that to y2. x2, let's put that to y1. x3, we'll put that to y3. Okay, so I built this to be surjective and injective. If I left anything out of y, it's not surjective. If two x values go to one y value, it's not injective anymore. Okay, but this is specifically designed to be injective and surjective. Okay, so what do we notice? In constructing it, number one, we've used everything in y, and it goes 1 to 1. So we can look at the two sets, and we can pair the elements up. x1 and y2, that's one pair, right? x2 and y1, that's another pair. x3 and y3, that's another pair. You see how we have this correspondence between everything in x and everything in y. We have a 1-to-1 correspondence between everything. So what mathematicians use, we're not going to get into this, but it goes into the idea of cardinality. So here we say that these two sets have the same size, right? Because everything in this element gets mapped 1-to-1 to everything in that set there. So if this set had 3 elements, that set must also have 3. Because we can't leave anything out, and it goes 1-to-1. If this set had 5 elements, that set would also have 5 elements. Why? Because we can't leave anything out, and it goes 1-to-1. So each thing in here goes to one and only one thing in there. Okay, so in that case, we're not going to get into this too much, but we say that the sets are isomorphic. Okay, fancy word, it just means that they have the same number of elements. Okay. Okay, so we say that x and y are isomorphic. Okay. And we will see a few examples of these so-called isomorphisms. Okay. Okay, so it's just the name, don't worry about that. We will be more interested in proving these things. Okay, so let's look at our first example. Okay, so we've got this function here. We want to show that this is a bijective function. Okay, remember, bijective is injective and surjective. Okay. Is it injective? Yes. Okay, if you have doubts, just go from the definition. F of A equals F of B. 2A minus 1 equals 2B minus 1. We can add 1 on both sides. 2A equals 2B. We can divide by 2 on both sides. A equals B. Okay, so a quick check. Yes, it is injective. Next, is it surjective? So, for every element in the target, so that could be some element y from here, is there an x value that gets mapped to that? Yes, there is. I can tell you what that will be. So given a y in the target, so our claim, so given the y, you give me that y, and I'll say, I know an x value that gets mapped to that. Okay, so our claim x equals y plus 1 over 2 is that x. That's my claim. Okay, if my claim is true, well then it's surjective. Why? Because any element in the target has a corresponding x that gets mapped to it. We need to check that. Okay, I'm just claiming that there. Okay, so, well, how do we check that? Well, let's take the x value that our claim is the x value. We substitute it into f and see if we get y. If we do get y, it means that the x gets mapped to the y. If we don't get y, well then the x didn't work. Okay, so let's see, f of x. Okay, so we just use the definition here, 2x minus 1. Okay, but now in the place of x, I'm going to put what I claim to be the x that works. Okay, a little bit of algebra. The 2 and the 2, they cancel. So we're left with y plus 1 minus 1, which is y. Okay, so big surprise. You gave me a y value, okay, any y value, right? I just said y. I provided an x value that maps to the y value. Well, that's surjective, right? Okay, so you give me something from the target, I gave you something from the domain that maps to it. That's the definition for surjective. So it's surjective. Okay. Yes? Yeah, that's my claim. I'm just claiming that. We're going to get to how that comes about now. Okay, yeah, this was just my claim, right? I've just said that this was true. It is in fact true, but the question is, how did I get that? Okay, so how did I get there? Okay, the way we get there is with the inverse function. Okay, whatever you learned in high school about inverses, delete that. We're going to start from the beginning. Okay, no, I'm serious. The stuff you learned in high school, delete it. Okay, so let's say we have a function from x to y. And it's f. So I'm going to write it like this. Okay, so this is just any function from x to y. If the function is injective and the function is surjective, then the function is bijective. A function being bijective means that there exists an inverse function going from y to x. We write it as f inverse going this way. Okay. This only works, okay, going both ways like this, if it is injective and surjective. Okay. Now, when you did inverse functions in high school, you paid no attention to the domain and range. You were given y equals 2x squared plus x, and you were asked to find the inverse. Your teacher never gave you the domain. The teacher never gave you the range or the target. You just did the calculation. Okay, now we're going to see where that actually comes from. Okay, so we have f going from x to y. The domain is x, the target is y. F inverse, which exists because it's bijective, we know it exists, then goes from y to x. It has a different domain, it has a different target. It's another function, right? Okay. Now what makes it an inverse? We know from high school that inverses undo each other, right? Okay, so what does it mean for these inverses here to undo each other? It means that if we start off with an x element, we use f to get mapped to a y element. We then use f inverse to get mapped back into x to the same element we started with. That's what it means for that to be an inverse. Going in that direction. There's two ways we need to check this. So, f inverse after f of x takes us back to the same x. Okay, so you would have seen that before, them undoing each other. But that's only looking at it one way. We could look at it the other way. The other way is that f after f inverse of y is equal to y. Okay, you definitely didn't see that. Okay, why are there two? Because we can start from x, we can go with f and back with f inverse. Or we can start in y, go with f inverse and come back with f. There's two paths. In the first case, we say that it's a left inverse. There's f inverse on the left. It's a left inverse. Over here, this is a right inverse. Okay, because it's on the right. So sometimes we can have a function that is a left inverse, but not a right inverse. And we'll see examples of that. Sometimes it's a right inverse, but not a left inverse. Yeah, it depends on which way you're looking at it. If it's a left inverse and it's a right inverse, we just say left inverse. Okay. So here it is both a left and a right inverse, but sometimes it can only be one. You definitely didn't do that in high school. So that's why I say delete what you know. Okay, so how do we find the inverse? Okay, very easy. It's the same thing you did in high school. Okay, that method of y equals f of x, you swap x and y and then solve. That works exactly the same. The only thing we're adding onto here is we're paying more careful attention to the domain and the target. Okay, we're going to have to sometimes change the domain and the target so that the inverse exists. And we'll see that in this first example. Okay, so f of x equals x squared. Okay, in high school, you would take this and you would tell me root x, and that would be it. Okay, but that's wrong. Yeah, and we'll see why it's wrong now. Okay, so we can write it like this. F goes from the real numbers to the real numbers. X gets mapped to x squared. This is what you saw in high school, or what you assumed in high school. You have that the domain is all the real numbers, the target is all the real numbers, and you just calculated and you got root. But there's a problem. That doesn't work. And it goes back to what we had before with the root function. Okay. So let's say that the root function is the inverse, and we'll see there's a problem. So we want to go from the real numbers to the real numbers with the roots. With x squared at the top. Okay, that's fine, and we want to go back with the roots. Okay, right, this is the back and forth behavior that we mentioned earlier. Okay, so this is entirely wrong, but let's see why. Okay, going from the real numbers to the real numbers with x squared. That's fine. No problem with that. You can put any real number in, and you'll get some positive number out. Okay, so in this case, the target is not the same as the range. Right? But that's fine, right? It works going that way. What about coming back? We're taking roots of negatives. It doesn't work coming back. That's the problem with this. If you assume that the domain and the target are just real numbers, it doesn't work. Okay. So we need to fix something here. Let's try and fix the target so that it works. And then we'll see what happens. Okay, so going from the reals to the reals doesn't work. What will work? 0 to infinity. Okay, so let's try adjust this and see what happens. Real numbers, 0 to infinity. Okay, along the top path, I'm going to take x squared. Along the bottom, I'm going to take root x. And we'll see. With these adjustments, we'll get to the right answer. Remember, it's got to go this way and back, and the other way and back. Okay. So, let's start from the beginning and see if we fixed everything. Going from the real numbers to the positive real numbers with x squared. Is that fine? Yeah, that's fine. Okay. Going from positive real numbers to the real numbers with root x. Is that fine? Yeah, that's good. We're not taking the roots of a negative. What about the other direction? If we start from here, we go there and we come back, do we end up at the same point? Not always. Let's look at minus 2. Minus 2 from here. I can pick it, it's the real numbers. Minus 2 gets mapped to 4. On the return trip, it gets mapped to 2. I started with minus 2. I got mapped to 4. The root then took me to 2. Did I start at the same point? No. That's a problem. I do a round trip and I don't get back to where I started. But we said here, f inverse of f is x. F of f inverse is y. If I do the round trip, I should end up back where I started. So this doesn't work. Okay, we're almost there. What can I change now? Yeah. Okay. So let's change it a little bit more. 0 to infinity. Now I get mapped with root x. X squared. And then I go back with root x. Okay, now this works. I can do a full round trip, starting from where I like, and I end up back where I need to. So let's just do a quick example with the minus 2. I'm going to start from here, and I should end up back here with my 2. Okay, I can't pick minus 2. Okay, I've got that rid of that. 2. If I map that way, I end up at 4. If I come back, 2. Did I start where I left? Yes. Let's go on that side. I pick 2. I get mapped this way with root. Root 2, I end up over here, right? Started with 2, I end up with root 2. I then square it and I get? Did I end where I started? Yes. So it works. So you see how we had to change the domain and the range for this to work. Is it still injective? Is it still surjective? So it's fine. Okay, so what does this look like as a picture? Okay, so this was all thinking about sets and so on. Now, if we do it in terms of a picture, we get the answer almost immediately. But you need to understand why. Okay, so I'm going to draw the function there, and then I'm going to draw the inverse over there. Okay, so I'm going to draw x squared. Now, the domain for x squared, going that one, is positive real numbers. So I only have one branch of the parabola. I don't draw the other branch because it doesn't exist. It's not part of the domain. I don't care about it. Right? Okay, what about the inverse? That's the root function. It's also on the positive part, so it just looks like this. Okay, so here we have f, here we have f inverse, and all is good. Okay, so this is why we had to go through that whole process of changing the domain and the target. If we had both branches of the parabola, is it surjective? No. But we want this to have an inverse. So we change the domain so that it is injective and surjective and therefore bijective. If we included both branches, it's not injective. So that gets thrown out. Here we don't want to include the negative real numbers. So we make it surjective by getting rid of them. And then this goes to that one, and then that comes back to this. Okay. Now for homework, you're going to do the same sort of thing, but now instead of choosing that branch, I want you to go through the same procedure, but with the other side. Yes? Yes. Yeah. So we're restricting it there. Okay. So we go through this whole long process and we end up with this positive branch over here. Okay, I want you to go through the whole process again, so I want you to end up with something like this, okay, the domain and the range with x squared and root x, but now I want it so that it works for the left branch. You need to change some things around so that in the end we end up with the left branch, which is defined over the negative real numbers. There's a few things you need to change. Okay, so homework. Okay, so do the same process, but for the left branch now. Okay, so you should end up with that as your function. So, yes?
The inverse function work when it's bijective.
Yes. Yeah, inverse function only exists if it's bijective. Okay, so however you define the function, okay, remember you're defining the function, the domain, and the target. So you do whatever you need to do, but I want it for the left branch this time. Okay, good. Everyone understand the homework? Okay. And then another homework, you don't need to do any writing or anything for this, but just think about it. We're going to continue with that, with this bit next time. Okay, so how do we define the domain and target for f of x equals sine x for it to be invertible? Okay, why? Okay, so we've got the sine function. We know the domain is all the real numbers. Okay, like the default, you can think of it like that. So the default, the domain is all the real numbers. The target, all real numbers. The range is -1 to 1. That's like the default that you should have in your head. But that doesn't work if we want to find the inverse. If the domain is all the real numbers and the target is all the real numbers, inverse doesn't work. How should we change those two such that this does become invertible? And why do we make those changes? Okay, so you don't need to write anything out, just think about that. Okay, any questions about the homework? No questions. Okay, so tomorrow we will go over more of these examples on finding the inverse. So I'll give you a function with some domain, some target. That's the default function. My question will be, what should the domain be? What should the target be such that it is invertible, injective and surjective? And secondly, what is the inverse? Yeah. How do you find the inverse? You need to give me the function rule, the domain, and the target. Okay, so we're going to look at that next time.